All right, let's do another one. So now here I'm going to start doing examples that follow the examples in the textbook. So this is example 1 in 6.3 of your textbook, okay? And it's 2 sine x over 2 equals 1. You are welcome to look at the solution in your textbook to see if you like it better. Here's how I'm going to work this one out. So first of all, I'm going to start off solving for the trig equation. Okay, so in this case, we would divide by 2. And then I'm going to apply my handy-dandy rule, right? I'm going to say, all right, if sine x over 2 equals 1/2, then that means x over 2 is sine inverse of 1/2, right, plus 2n pi. Or x over 2 is pi minus sine inverse of 1/2 plus 2n pi, of course. Oh, we've done sine inverse of 1/2 so many times, right? But it's pi over 6 so 5 pi over 6 over here. And then to finish solving for x, in this case, we would multiply through by 2, right? So we get 2 pi over 6, which is pi over 3, plus 4n pi. Or x equals 5 pi over 3 plus 4n pi. Okay, so that's all of them. Right, that's all of the solutions. So we'd say, so all of the solutions are pi over 3 plus 4n pi, or 5 pi over 3 plus 4n pi, where n is an integer. But if you're just looking for the solutions that live between 0 and 2 pi, then you start plugging in some stuff for n. Obviously, if I plug in -1, I'm going to get something way too small. If I plug in 0, I get pi over 3. So that's in there. If I plug in 1, I get something way too big, right? I'm already at 4 pi plus pi over 3. It's way too big. Same thing goes for 5 pi over 3. If I plug in -1, way too small. If I plug in 0, I get 5 pi over 3. If I plug in 1, it's way too big. So those are all the solutions to that equation that live between 0 and 2 pi. Oh, that was short. That was a pretty quick one. Maybe we can just do another one in the same video. You think so? I think so. Let's do another one. This is example 2 from 6.3. So this one says cosine 2x equals cosine x. Okay. Now, what's challenging about this one is you need to rewrite this in terms of just a single trig function. And, you might think, oh, well, we just have one trig function. We just have cosine, right? Except that you have cosine 2x on the left-hand side and cosine 1x on the right-hand side. That is a little complicated. So I think the best way to try to do this is to rewrite one of these functions so that it's cosine of the same multiple of angle. In other words, we either need to try to rewrite cosine x as something in terms of cosine 2x, or we need to rewrite cosine 2x as something in terms of cosine x. And I think we have a little bit more luck with that second approach because we have all kinds of identities for cosine 2x, and one of them, right, one of those double angle identities just so happens to utilize cosine x, right? And it's this one that says cosine 2x is really the same thing as 2 cosine squared x minus 1. Right? So that's the equation that we have when we make that replacement with that double angle identity for cosine. Now at this point, this problem is just like a problem from 6.2, right? From the lecture that we did yesterday. It's just exactly the same as one of those types of things. The idea is move everything over, factor. If you can't factor, then use quadratic formula. Okay, well let's try it. Okay, I'm going to try to factor this thing. Okay, so I know that to get 2 cosine squared, I should have 2 cosine in one of the groups and cosine in the other group. And then in order to get a -1 here, I have to have a 1 in both of these places, and I need to have a positive somewhere and a negative somewhere. If I put the positive here and the negative there, I'm going to get a -2 cosine x and a +1 cosine x. Those are going to combine to give me a negative cosine x just like I want. So I think that's the correct factorization. Okay, now we apply zero product property. So we can say if this times that equals 0, then either this is 0 or that is 0, right? The only way you're going to get a product to equal 0 is if one of the factors is 0. So we're going to say 2 cosine x plus 1 equals 0, or cosine x minus 1 equals 0. Okay, so here we get 2 cosine x equals -1. So cosine x is -1/2. Here we get cosine x equals 1. Starting to run out of space, but oh man, we're going to get all kinds of solutions here, aren't we? So for this one, we're going to get, okay, if cosine x is -1/2, then that means that x is either cosine inverse of -1/2 plus 2n pi, of course, or x is 2 pi minus cosine inverse of -1/2 plus 2n pi. If cosine x equals 1, then x equals cosine inverse of 1, right, plus 2n pi, or x is 2 pi, x is 2 pi minus cosine inverse of 1 plus 2n pi. Okay, well let's finish this up. Now I'm going to come back up here to finish this out. All right, so I've got x equals cosine inverse of -1/2. Well, let's see. I'm thinking that's 2 pi over 3. So that's if x is cosine inverse. It could be x is 2 pi minus cosine inverse of -1/2. 2 pi minus 2 pi over 3. So this is 6 pi over 3 minus 2 pi over 3. That's 4 pi over 3. Or, x is cosine inverse of 1. Cosine inverse of 1 is 0, right? So this is 0 plus 2n pi, or 2 pi minus 0, which is just 2 pi plus 2n pi. Now this is interesting. Notice these last two solutions are exactly the same. Okay, you may have to squint at it just right, but if you think about all of the solutions that these two rules are going to generate, it's the same set of solutions. Okay, so this one, if I plug in 0 for n, I get 0. This one, if I plug in -1 for n, I get 0. On this one, if I plug in 1 for n, I get 2 pi. On this one, if I plug in 0 for n, I get 2 pi. On this one, if I plug in 2 for n, I get 4 pi. And this one, if I plug in 1 for n, I get 4 pi. Right? So they're going to generate the same list of solutions, right? So you don't get any additional information by considering that second case. And here we can simplify this further and just say, well, 0 plus 2n pi is, of course, just 2n pi. So if I'm thinking about all of my solutions, they would be 2 pi over 3 plus 2n pi, 4 pi over 3 plus 2n pi. Sorry for writing so small, I'm trying to cram it all in. Or just 2n pi, right? Where n is an integer. If I'm looking for the solutions that live in the interval from 0 to 2 pi, then I do my old trick of plugging in numbers for n. If I plug in 0 for n, I get 2 pi over 3. If I plug in 1 for n, I'm too big. Here, if I plug in 0 for n, I get 4 pi over 3. If I plug in 1 for n, I'm too big. Here, if I plug in 0, I get 0. If I plug in 1, I get 2 pi, and that's too big. Right? So those are all the solutions that live between 0 and 2 pi.